The learning target for this lesson is to apply integrals to find the area of a region. And you may be thinking this is a learning target we've already accomplished because one of our first interpretations of the integral was to find the area between a function and the x-axis. But today extends that idea a little bit by finding the area between two functions. So here's the concept that we're already familiar with. We take the integral from a to b of f of x, and that gives us the area between the function f of x and the x-axis on an interval a to b, which are both x values, and that's represented here in this graph. So we've shaded in all the area between the function and the x-axis. What you didn't realize at the time was that you actually were finding the area between two functions. It just so happened that the second function was the x-axis, and that function is represented by g of x equals 0. So when we extend our idea to the area between two functions, we are now going to have a secondary function here besides 0 that we have to represent. So it becomes the integral from a to b of f of x minus g of x, and that gives us the area between two functions. We see that here represented in the graph, so we've shaded in only the area between f of x and g of x. And mathematically what happens is that the area under g of x gets subtracted, so it subtracts the area between g of x and the x-axis. It's really important that we do the subtraction in the right order, otherwise our area will come out to be negative. So in our picture here, the f of x function is the greater function, and we subtract g of x, which is the lesser function. Another way to think about it, and this might be easier to remember as well, is that you always do the top minus the bottom functions. Let's take a look at setting up our first example, and you'll notice right away we're not given a graph to look at, so sometimes we are and sometimes we're not, and when we're not, we have to set up our own sketch of a graph so we can get a visual of which is the top and bottom function. The easiest way to get started sketching your graph is to look at your a and b values, so your x interval from 0 to 1, make a quick xy chart for each one, plot the points, and then connect the graph. So for the first y1, I knew it was a parabola, so it's more curved, and the second function is linear, so that's a straight line segment from 0 to 1. So I've labeled each graph so I won't forget which one is which, and I've shaded in the area between them, which is what I want to find. And I want you to recognize that I shaded in with vertical lines because in a couple examples we'll realize that we are not always going to use a top and a bottom function, that sometimes we'll have to shade horizontally. So that's just a foreshadow of what's coming. So now that we have a picture of our graphs, we can go ahead and set up our area integral from 0 to 1. Our top function is that piece of the parabola, x squared plus 2, minus our bottom function is the linear negative x dx. And in this next step, all I've done is a little bit of simplifying to get ready for my antiderivative. Be careful here, you've got a minus negative, so that gives you a positive x. Then since it's just a polynomial, I took the antiderivative of each term separately, and I'm going to evaluate that from 0 to 1 using the fundamental theorem. When I substituted my 1 into my antiderivative, I got 1/3 plus 1/2 plus 2. Substituting in the 0 gave me all zeros. So my final answer for the area would be 17 over 6 when I get a common denominator. Remember, you could actually stop on a free response question here. You don't have to do the rest of the arithmetic after you plug in your limits. I'd like to save examples 2 and 3 for us to talk about in class, so let's jump down to example 4. Example 4 uses a strategy that you can employ when you come across a graph that's perfectly symmetric and you have symmetric regions. So instead of finding the area of the entire graph, you can take one of the symmetric regions and just multiply it by a constant multiple. So when you see this graph here on the right that represents this y squared function, you can either see 2 symmetric sides or even 4 symmetric regions. And we're going to see it as 4 to solve this problem. I think that's the easiest way, so that we're using just one piece of the function and the x-axis as our second function. To find the top function of the region, we just had to quickly take the square root of both sides of this equation. And notice we're only using the positive square root of that function. The negative square root is what creates the bottom half of that region. So to set up my integral to solve for the area, I'll first remember that I have 4 symmetric regions, so I need to multiply my integral by 4. I see that my x-interval is from 0 to 2 of that positive square root function. And since this is a calculator question, I'll go ahead and set that up in my Math 9. Notice I put the 4 in right at first, and you can follow that directly with the Math 9 function to get your integral. And the final answer would be 10.667 if you round to 3 decimal places. You'll notice that the example 5 is also a calculator question, so I can use it to come up with a sketch of my region, so I don't have to use an XY chart. The first thing I notice is that it's going to be the area in the first quadrant. It's got 2 functions that I need to put into y1 and y2, and it's also bounded by the y-axis. And so that's a third function that'll become a boundary, so that'll help us decide what that area region really looks like. So let's get that into our calculator. So you see I have the functions in my y1 and y2. I also went into my window and kind of played around with those values. I knew x-min and y-min should be 0 since I'm in the first quadrant. And I also noticed by graphing it a couple times it was a really small function, so I made my x-max and y-max both 2. So if you'll do the same, we'll be looking at the same graph. And you'll notice you have kind of 3 regions that you're looking at, so it's really important that we know it's between the 2 functions, which could be either here or here. But that third bound of the y-axis really makes the decision for us. The y-axis is the third boundary, so we're looking at this kind of triangular region here. So our next job is to find this intersection, which will give us one of our limits on our integral. So using my second trace intersect, I came up with an x value of 0.941. So that will be my upper limit on my integral, and I know that the area starts in the first quadrant at 0. So I went ahead and just made a sketch of my graph on paper so I'd have it, and I wanted to determine and label which function was which. So the e function is the top border of my region, the 1 minus cosine is the bottom border. I also noticed I hadn't rounded correctly, so I just added another decimal to my x value, and notice I didn't even copy down the y value because the x is all we need for that upper limit. So set up my integral with the top minus bottom function, the e function minus the cosine function, and I notice I have this really tricky subtraction that I'll have to distribute, and I really don't want to take a chance on typing that in incorrectly or making a distribution mistake. So I'm going to go ahead and use the fact that my functions are already in my y1 and y2 and use that in my Math 9. So I'll show you how to set that up. So once I'm in my Math 9, I've got my limits typed in, and I want to access those functions in y equals. I actually use the alpha shortcut, so alpha trace will give you a list of those y functions. So I decided that my e function would go in first. So fortunately, I labeled that as y2. So I'd say y2 and then minus, and you would do the same shortcut, which is alpha trace, to get the y1 in there, and then dx. And that gives me a final answer rounded to 3 decimal places of 0.591. So that's just a really good technique to keep in mind on lots of different situations where you want to save time and also making careless errors. If you've got that function typed into y1 or y2, you can use those alpha trace shortcuts to make your life a lot easier. So we'll save the rest of those examples for class.